continue with our topic, which is matter and materials. Today we will start studying about compressive and tensile forces. For example, if you have a material or a body like this one, if you want to shorten it, it means you will compress the material. You apply a force like this, and this material will be shortened. So these forces applied to make an object to be shortened or to be short, it is compressive force. And if a material, if you apply a force like this in a material, it means you are stretching it, you make it long, that is tensile forces. So this is how we can describe compressive and tensile forces. And also, one example is when you have a spring like this, you see, which its length is L here, before you apply a force. But if you apply a force, you see, if you apply a force here down, if you apply a load down, it means this spring will be pulled down, will be stretched, its length will increase, so it will be like this. You see, so the original length was here, but now it has increased. So the increased length is known as extension. So we have the original length and the increased length, which is extension. You see, so this is to say that this is after applying tensile forces. The body is stretched, so the extended length is extension. So what is extension? We say extension is an increase in length, after the length of the spring, after applying force. So that is extension. And also we can plot a graph of this extension and the force, because without applying a force you cannot get extension. So for the spring to extend, you need to apply a force. So now we can see how we can plot a graph. We can use this graph. This is applying force, and this is extension of an object after applying force. You see, if your graph is straight like this, you see, and this is O, this is A. In this way we say that now extension is then proportional to the applying force. Extension is direct proportional to the applying force. So if a material obeys this relationship, say this is Hooke's law. If a material extends, its extension is direct proportional to the applying force, we say this material obeys Hooke's law. But if a material goes beyond this point A, at this point A, let's say this is B, we say material does not obey Hooke's law. This point from A to B does not obey Hooke's law, because its extension is not very proportional to the applying force. But if we want to find here a gradient, we find that our gradient here is equal to change in y, which is change in force, over change in x, which is change in extension. So it will be force over extension, force over extension, force over extension. So this force, this gradient now, we call it stiffness. Stiffness or force constant, which is equal to force over extension. Force over extension. That XC, which is extension, is that proportional to what? To force. So extension is equal to K F. If you want to remove this quadratic sign. So our K here is force constant, which is stiffness, will be equal to force over X, which is a gradient of the graph. So we can also find stiffness by plotting a graph, which will take a gradient of the graph to give us a force constant. So a material obeys Hooke's law if the extension produced in it is proportional to the applied force. If you apply a small force to a spring and then release it, it will return to its original length. This behavior is described as elastic. So elastic is when you apply a force. You see, you apply a force. For example, this is a spring. You see, so after applying a force, it will stretch. But if you remove this applied force, it will return to its original length. So this material, we say it is elastic. But if you apply a force and an object stretches it, but when you remove a force, the material is not coming back to its original length, we say that material is already deformed. So if you apply a larger force, the spring will not return to its original length. It has to become permanently deformed. So elastic is when you apply a force to an object. It's when you remove and apply the force to an object and return to its original length. Now let us see the elastic limit. This is the force beyond which the spring becomes permanently deformed after applying larger force. That is elastic limit. Elastic limit, like this. Force tension. Elastic limit, like this way. Here. Okay, this is elastic limit. It's a point. This is the force beyond which the spring becomes permanently deformed after applying a force. Now let's see one over question. Example, we have this graph here. Force, this is force, this is extension. Okay. This is D, this is B, and this is C. this is A. So the first question says that state which spring has the greatest value of force constant. Which spring has the greatest value of force constant? You see, which spring has the greatest value of force constant? You see, refer to force constant. It says force is equal to force constant is equal to force over extension. So we have to look here which line has the larger force. We take this one, so we take this one, you see, this one is small. So the larger force here is D. Also we have to find which is steeper. Which is steeper? The steeper is this one. So remember that force constant is equal to gradient. So the larger gradient is the larger force constant. So D will have the what? Force constant. The larger force constant. Because see, this is curve. It means the gradient is changing. And state which is the least steep. It means this is A. A is the least steep. State which of the four springs does not obey Hooke's law. Which of the four springs does not obey Hooke's law? Spring D, it means X is proportional to force. Spring B, X is proportional to force. So this obeys. But in C and A, spring C and A, the extension is not proportional to the applying force. So C and A does not obey Hooke's law. Does not obey Hooke's law. Stress and strain. Stress and strain. Strain. Okay, now by starting strain. Strain we say is a fractional increase in the original length of the wire. In the original length of the wire. You see? So fractional strain. Fractional. So strain is represented by this symbol, which is sigma, is equal to fractional. It means the extension over original length. Extension over original length. This fractional is what known as strain. And stress this is a force applied per unit cross-sectional area. Force applied per unit cross-sectional area of the wire. So stress this is equal to applying force per cross-section area. This is stress. Okay, come back here to strain. Strain has no unit because the extension its unit is meter and the extension of lungs its unit is meter. So they cancel it out. So which is this is unitless. But stress, this will be Newton, this will be meter square. So the unit of stress is Newton per meter square. So there is an indication of stiffness of the strain of the material, and an indication of stiffness of material is known as Young modulus. Young modulus. This is an indication of stiffness of material. It's given by strain over stress. Strain over stress. No, serious. It is stress over strain. Stress over strain. Stress is sigma and strain is epsilon. So Young modulus is equal to stress over strain. It is sigma over epsilon. So this is your Young modulus. So we also, and the unit of Young modulus is same as stress because strain has no unit. Stress has no unit, so the unit of Young modulus will remain the same as stress. So we can also stretch a graph of stress against strain. This is strain and this is stress. So if you find a gradient here, the gradient for this graph is equal to stress, change in stress over change in the strain. So the gradient is equal to Young modulus. Young modulus. So let us finish our topic, which is matter and materials, by looking elastic potential energy. Whenever you stretch a material, you are doing a work. This is because you have to apply a force, and the material extends in the direction of force. So when you apply a force, you transfer energy to the material. This energy is called elastic potential energy. You see, for a material to stretch, you have to apply a force. So when you apply a force, it means in a certain distance, in the direction of that distance, that increased distance is, for example, the spring. After applying a force, it will stretch. So that increased distance extension x will be directed to the applying force. So because there is a force and the distance, so it means we are doing work, because work is equal to force times distance. And when you apply a force, it means you transfer energy. That energy is what called elastic potential energy. This energy is called elastic potential energy, or strain energy. See, because work done is equal to force times distance in the direction of force. You apply a force in the spring, extension happens. So work done will be equal to applying force times distance, extended length. So our work done here is force times distance in the direction of force. So for example, this graph of force against tension. Okay. For example, also A obeys Hooke's law. So if we make here a triangle, So our work done in stretching or compressed material is always equal to area and the graph of force against the extension. So if we find the area here of this section to be equal to work done, So area of triangle is equal to half times base times height. So our base here is x, it is extension. Our height here is f. So work done will be equal to a half x f, extension times force. So remember that from force constant, we say that K is equal to force over x. So now force is equal to Kx. So we can say work done is equal to a half times x, but force is equal to Kx. So our new formula of work done by involving force constant or stiffness is equal to x square k. A half is equal to kx square. This is the elastic potential energy. We can use this formula here, which is a half times extension times applying force, or a half times extension times force constant times extension square. Okay, thank you very much.